Could I get started, or you say a couple words, James, first?
All good on my end.
Okay. Okay, great. So we are on hour. So it's a pleasure to introduce our speaker for today, Ben Tutolo. He is associate professor at the Department of Earth, Energy and Environment at the University of Calgary in Alberta. And Ben originally from USA. He did his bachelor degree in Penn State University, followed by PhD at University of Minnesota. I guess working with Bill Seyfried on a hydrothermal system, probably from lab work as well as sort of going on uh, ship cruises. And then he continued with postdoc at University of Oxford with Nick Tosca, sort of advancing more into, I guess, Precambrian stuff, and as well as working on clays and hydrothermal systems. He then studied as an assistant professor at University of Calgary, where he's based now. And in his research, he works on interaction between rocks, water, and gases that affect life on Earth and potentially Mars. Since 2022, he has been working as a science team member on Mars Science Laboratory Curiosity rover mission to Mars. And he received Mineralogical Society of America Award, its early career award. And in 2022, since he got this award in 2022, and he has been serving as the secretary of the Geochemical Society and associate editor of GCA since 2023. So with this, I pass to Ben, and we're looking forward to your talk.
Yep, thanks a lot, Andre, and thanks everyone for showing up. I always watch the VSPG seminars on YouTube because I almost always teach at this time, but fortunately the semester ended last week, so I actually am able to give the talk today. So, investigating early Earth hydrothermal processes to understand fluxes on habitable worlds beyond. I was originally invited to give a talk on this subject at the 2023 AGU Chapman Conference in Cyprus, and then they called my bluff by making me write a chapter about it, which is basically what I'm going to summarize in this talk today. So the big outstanding question here is what might control hydrothermal fluxes on billion-year timescales in the Precambrian and also on habitable exoplanets. So as we look beyond our Earth using the James Webb Space Telescope and Hubble and others, we are learning more about life in the universe than, or the potential for life in the universe than at any time in human history. But we only really have an N of one, an example of one here of a habitable environment that did originate life, and a lot of that must have happened during the Precambrian. So I like to start with this quote from Ray Seaver. It's in a book, which is cited there at the bottom. And he says, deducing the weathering and sedimentation regimes of the early Precambrian is a disease caused by a virus, which is only a slight mutation of that which causes otherwise sensible scientists to calculate the composition of the early Earth's atmosphere and oceans. So here I am mutating that disease one step further by trying to think about the hydrothermal systems, not just weathering on early Earth, which have essentially very limited rock record. But to guide this quest here, we like to use this concept of habitability. So this is again on the left-hand side here. You can tell that we only really have one example of life, and that's life here on Earth. And we have been and know more about Mars and the surface of Mars and its potential of originating life, and we haven't yet discovered any real evidence for life there yet. So a habitable environment is a place where the ingredients, so carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, the energy, so light and heat, the conditions, temperature and pH, and the solvent water all coalesce into one particular environment, and we call that environment habitable. And so we know in some ways that early planetary systems must have hydrothermal systems as their cooling, and in a way, the hydrothermal systems must be contributing to the habitability of those environments. And that's a lot of what I'm going to talk about today. Okay, the habitable zone depends on the star. Again, our star has been getting brighter through time, and we obviously started with a much cooler star early on, 30% less bright than it is today, and has become brighter as time goes on. And so where we're at is essentially at the center or around the middle of the habitable zone, and it's thought perhaps early on in Earth's history that we are sort of at the edge of the habitable zone because our sun would have been much less bright. And indeed, Mars would have been potentially outside of the habitable zone based on what we know about atmospheric systems today. And as our sun has gotten brighter, obviously Earth has somehow maintained habitability through that time and maintained liquid water oceans, whereas Mars, our most definitive contrast, has clearly lost habitability through time. And so part of what I want to talk today about is how Mars and potentially Earth might have been made habitable by hydrothermal systems early on in their history. Okay, so this is just one of a bajillion models. This is the Halevian-Bacon model, which I point to for various reasons, and as you'll see in a minute, that liquid water on the early Earth apparently required high partial pressures of CO2. So on the left-hand side there, they've got the axis going from youngest to oldest, left to right there, and an estimate based on their Monte Carlo simulations for the partial pressure of CO2 through time. So starting, 4.5 billion years ago, having partial pressures of CO2 up near zero point 0.1 bars, and then obviously declining through time towards what it is today. And interestingly, that contributed to the pH of the oceans, which in some way impacts the hydrothermal systems that were also interacting with the oceans. And I also note at the bottom there, Josh Chrysanthemum-Totten had a really great VSPG earlier this semester on this subject. Okay, so one interesting point that I want to make here early on is that unless ocean alkalinity was unexpectedly much higher, so this is the so-called soda oceans that sometimes folks talk about, which I think has been largely disproven, high partial pressure of CO2 would require high calcium concentrations in seawater. So just to zoom in on here, and this is the reason I like Halevian-Bacon's model, because they have essentially a model for all of the major cations and anions in seawater. If you zoom in on alkalinity here, we don't expect alkalinity would have been much higher through geologic time. And if that's the case, having a high partial pressure of CO2, just by the rules of the way that PCO2 and alkalinity work, calcium carbonate solubility must have been much higher on the early Earth. So the base water that would be entering into Precambrian hydrothermal systems would have been much more calcium rich than on Earth today. So their estimates are on the order of several hundred millimoles, so on the order of 5 to 10 times more than what we would expect today. So if calcium was much higher, the reaction zone, so in our classic schematics of hydrothermal systems shown in this paper led by Drew Severson from last year, where we have fluids entering into the oceanic crust, interacting in some deep system or deep part of the system, getting heated up to on the order of 400 to 500 degrees, and then venting at the seafloor. We know this as the reaction zone, or the RZ here. And the reaction zone is largely thought to be buffered by this equilibria. Anorthite plus tremolite plus 6H plus goes to chlorite plus 3 calcium plus quartz. If we just take away and assume that the activities of the minerals are 1, which there's many good reasons to do that, we end up with this sort of equilibrium here between calcium and H plus. So if calcium was indeed much higher in Precambrian seawater, then we would expect also H plus activity to be much higher in Precambrian seawater or in Precambrian vent systems. And so low pH tends to increase metal solubility. We know this, for example, today in back arc basins where we have very low pH, very acidic pHs, and lots of metals fluxing out of those systems. And we would expect that on the early Earth as well. But stay tuned for some interesting other parts of those systems that I'll talk about. Okay, the other thing that we can say today is that calcium to sulfate ratio does have a clear effect on the chemistry coming out of the vents relative to modern systems. This would have been different in the past, and we know even over Phanerozoic time, calcium to sulfate ratio has changed, and therefore we expect that the emissions from black smokers would have changed. But this is the classic data from Bischoff and Seyfried in 1975. I apologize for the font size here. They didn't have size 28-point font back then. But if you notice that as we heat the fluid above about 150 degrees Celsius, we tend to precipitate calcium and sulfate. Eventually, we also tend to precipitate magnesium as clay minerals, but the calcium and sulfate is what I'm focusing on just now. So sulfate being higher than calcium in modern seawater means that as the sulfate is being precipitated here as anhydrite, which is retrograde soluble, the calcium is being depleted such that at high conditions we would have had significant or high elevated conditions we would have had most of the seawater calcium being removed as calcium sulfate and some sulfate remaining, which then goes on to be reduced to make sulfide minerals. And indeed, that's the part where anhydrite precipitates. And we could see this. This is one of my students, Simone Pugliati, from another number of years ago. You can go to, for example, the Transatlantic Geotraverse or TAG hydrothermal mound and find loads of pyrite and anhydrite in that mound, as we see in this picture here. Okay, but the other thing that we know quite well is regardless of your model for the history of atmospheric oxygenation, low atmospheric oxygen is expected before about 2.5 billion years ago. And so low atmospheric oxygen in the Archean likely resulted in low sulfate in Archean oceans. And again, on the right-hand side here is just a model of that from Kip and Stoichen from 2017, where we expect sulfate concentrations in Precambrian seawater to be on the order of 10 micromole or so at the most, and probably even less than that in some situations. And that's all due to oxygenic weathering of sulfides not occurring to the same extent as they do today. And indeed, if we go and look, there's not a ton of data on this, and it's partially biased by the fact that sulfates are hard to preserve in hydrothermal systems because they are retrograde soluble. So once we lower the temperature of them and make them into ophiolites or greenstone sequences, those sulfates can redissolve. But this is a paper or an abstract from Houston and others in 2017, which as you go from older to younger in the VHMS class, volcanic hydrothermal massive sulfide systems, you can see older ones, so Archean sulfide systems, tend to have different mineralogy. There tend to be more mafic dominated systems, very little of the siliciclastic felsic systems, which has evolved through time. And at the same time, the sulfide mineralogy that we precipitate has changed, again, potentially due to that amount of sulfate from seawater that's entering into the hydrothermal systems and being reduced to form sulfide minerals. And if we go and look at the sulfate abundance in these deposits from Archean to modern, what you can see is that we do see in general that the number of deposits that has sulfate preserved in them has increased through time. And again, this record is at least slightly biased by the fact that sulfate's hard to preserve in these hydrothermal systems, but that is at least an indication that we wouldn't have had exactly the same geometry and mineralogy of hydrothermal systems in Precambrian time as we do today. And so it's thought that anhydrite precipitation in hydrothermal systems today provides an insulating mechanism, so an interesting feedback mechanism on the actual venting process itself. So this is recent work published by Angus Fotherby, who is a student working with Sasha Turchin, and it was published in GCA earlier this year. So you can see as we go from left to right across the page, we have the temperature profile. So what's happening here is this is a 2D model of a hydrothermal system where the vent is here on the left-hand side, and water is circulating from seawater down, interacting with the hot hydrothermal or hot volcanic intrusion part of the system, and then venting. And again, there's a permeability contrast between the rocks that are there, so between the pillow basalts and the sheeted dikes in the system. And you can see the flow pathways here of those fluids. And indeed, once those fluids hit that 150, 200 degree mark, which was again constrained originally by Bischoff and Seyfried in 75, you can see that anhydrite precipitating. That anhydrite tends to block up porosity and permeability, and indeed focus flow such that it goes into a more focused venting system at the seafloor. So low Precambrian seawater sulfate likely affected the geometry of hydrothermal circulation. So again, a very simplified version of this from Fabrice Fontaine suggests that we have this anhydrite shell, which is more or less blocking the fluid flow through this zone, again, tending to uh, fill up porosity, decrease permeability, and then as that fluid circulates, it all vents through this narrow conduit, which then makes the narrow vent system at the seafloor. So you can imagine if we have very low, so 10 micromolars at the most, sulfate in Precambrian seawater, we would probably not have this so-called clogged anhydrite shell in Precambrian hydrothermal systems, which is a meaningful conclusion, or at least meaningful implication, because if that's the case, then we wouldn't expect focused flow and focused venting at the seafloor. We might expect a different form of the sulfide mineralization at the seafloor. And again, this is a sort of a contrast here. And again, there's not much evidence in this in the monograph chapter. I suggest that this is a useful line of investigation because that really hasn't been looked at in this way. But if you look at the left-hand side here, this is the geometry of the modern transatlantic geotraverse or TAG hydrothermal system. And it makes a mound-type morphology. Again, flow is focused, and then fluids vent at the seafloor and make this large collapse breccia mound structure at the seafloor. But if we look at other places from before the sulfate increased in seawater, for example, the Kidd Creek mine in Ontario, we tend to have these repeated lenses of sulfide mineralization, tend to be flatter, more lens-shaped. Again, likely or potentially because of the fact that we're not focusing flow in the same way that we do at the mid-ocean ridge hydrothermal systems today. Perhaps it's more stratabound and it occurs simply at the interaction between warm hydrothermal fluids and downwelling seawater. Okay, and also, so again, this hasn't really been modeled in depth, but it is an implication that has come out of at least recent studies. This is, again, Drew Severson's work from 2024, where we worked to try and model, based on seafloor spreading rates, the transition metal fluxes from the mid-ocean ridge system over the last 160 million years or so. And as you can see, the amount of sulfur, iron, and copper here all sort of depends in some way on the amount of slow, fast, and ultra slow spreading ridges or ultra fast spreading ridges that we have on the seafloor through time. And again, we see some peak at some point in the past and some depth. And so we expect if if we do have plate tectonics on the early Earth, and more on that soon, then we would expect there to be variations in the amount of mid-ocean ridge flux of these metals. So we only did iron and copper here because it's the only ones that we have in our database today. But you can imagine other allied minerals or elements like nickel and zinc also would behave along these same lines. Things that are going into the sulfide minerals in the hydrothermal mound would have likely varied as a function of spreading rate. So not only did, as I mentioned before, did the likely lower pH of the hydrothermal venting fluids on the early Earth potentially impact the solubility of these metals. It also, depending on the spreading rate, which again, largely based on whose model you're looking at, is thought to be earlier or faster on the early Earth than we would have also expected more metal fluxes to seawater from both of those standpoints. Okay, whoops. Iron formations are another important consequence of low seawater sulfate. This is the only actual field photo I have of a BIF, so I decided to use it. This one's in northern Minnesota at the Sudan mine. And so we know that these are perhaps one of the most interesting records of ocean chemistry from this time in Earth's history. And the fact that they're iron rich and tend to be sulfide poor is telling us something about the interactions of the minerals that form these rocks and ancient seawater. Likely the fact that there might have been less sulfate and then sulfide coming out of hydrothermal vent systems. So I put Birger Rasmussen's 2023 paper and then his ancient Goldschmidt abstract. I don't know what that's from 2015 again. But as you know, there's a large debate here in the literature right now about greenolite being part of and a primary mineral in banded iron formations. And I think this is kind of just a cheeky title here. Greenolite first, making BIFs green again. You can imagine having greenolite potentially as an initial portion of Precambrian iron formations. And Nick Tosk and I, now this is 2 years ago, published this paper where as we mix a hydrothermal fluid, which would have been generated in a Precambrian hydrothermal system, and you can go to that paper for the very painstaking effort that we put into deciding on how to exactly to model that, that as we vent and mix with seawater. So the first thing that precipitates is pyrite, very much the same as today, but because there's less sulfur in that water, the sulfur gets exhausted, the hydrogen sulfide gets exhausted quite rapidly. And then as we continue to mix, depending on indeed the dissolved inorganic carbon concentration of sulfate or seawater, the amount of greenolite that we precipitate becomes substantial again upon increased mixing. So again, it's not that there was no pyrite precipitating in these systems, or we don't expect that. And indeed, you can go to many Archean VMS deposits and know that there was sulfide precipitating in these deposits. But we do expect, because of the lower seawater sulfate, that we would have had higher fluxes of iron that then bonds with the silicon upon mixing with seawater to make the mineral greenolite. So sulfides indeed precipitate near the vent, while greenolite remains stable across the basin. So the pyrite will precipitate near the vent, and again, the geometry of this is currently up to debate and into speculation. I think it's valuable to try and understand how the lower sulfate might have affected the flow geometry here. But in any case, pyrite is much more dense than these other minerals listed across the top here. So even if it is being produced as a mixing product of vent water and seawater, then we expect it to rain out of the water column quite rapidly near the vent, which is indeed what we see happening today, but also in ancient deposits when we can look at Gossans, for example. And then as the fluid is being blown across the basin by background currents, we can imagine that iron siderite or iron carbonate is falling out of the plume. Eventually, greenolite and apatite minerals can be carried along and precipitated out or rained out onto the seafloor as sediments as well. And this is work from Serhat Sevgen in my group published earlier this year, just trying to understand if the hydrothermal greenolite is formed upon mixing with seawater, how stable would this be as it moves across the ocean? And I know this is a bit of a confusing diagram, but basically what Serhat did was say, well, if we go back to the original hypothesis from Tosca and others in 2016, and we precipitate greenolite basically as a nucleation product during low temperature precipitation or low temperature interactions in seawater, then we would expect that to be supersaturated. And his data show that greenolite will continue to grow as it moves across the ocean basins. But at the other side, if we are above the thermodynamic limit for greenolite solubility, but not quite to that critical supersaturation originally constrained by Tosca and others in 2016, we will still indeed dissolve a little bit of greenolite to end up making iron silicate stable. So all this to say is that the iron silicate that could come out of the vents in Archean hydrothermal systems likely was stable as it moved across the basins and is accumulating silica on its surface, which then allows it to be preserved as we see in chert deposits and jasper deposits. Okay. So again, we also have data from the modern oceans. This is one of many transects that we've seen from geotraces where we can actually look, this is the East Pacific Rise system, where we can see iron moving across, as particulate matter, moving across the oceans and ultimately potentially being bioavailable, or in our case, as we were discussing, precipitated as a component of iron formations. Okay, hydrothermal systems also produce hydrogen. So this is, changing gears a little bit to try and think about how hydrothermal systems interact with the atmosphere. And this is another potentially important greenhouse gas. So I started with talking about Halevi and Bacon's model for high CO2, giving us high calcium, but also high hydrogen fluxes from Precambrian hydrothermal vents might have contributed to atmospheric redox and also could have potentially done similar magic on Mars. So this is just a model for ancient Mars. So even with very high, up to 2 bars of CO2 pressure, Mars apparently needed an extra kick from hydrogen gas to be warm and wet. So here we see these cycles. This is from Robin Wordsworth's study from 2021, cycles between oxidizing and reduced atmospheres on ancient Mars. And it's thought that the only time that Mars was actually warm enough to stabilize liquid water, certainly before 3.5 billion years ago, is the periods at which we have a reducing atmosphere in these blue spikes here. So what happens is that hydrogen gets into the atmosphere, bounces off of CO2, and through that process, so hydrogen itself is not a greenhouse gas, but when it collides with CO2, it absorbs heat, and that is, or absorbs infrared radiation, and that is a mechanism of warming hydrogen, or warming the early surface of Mars. And it also has been proposed by earlier work as a potential warming mechanism for early Earth, when again, our sun was much less bright. So warm, wet, early Mars and potentially also early Earth apparently needed hydrogen to trap heat. And the question is, how do planets make hydrogen and also at the same time methane, another important greenhouse gas? Serpentinization systems is the first thing that comes to mind, and that's mostly because that's what I study. But we can also imagine potentially volcanic systems making hydrogen depending on the redox state of the mantle. So this is just a schematic diagram of how serpentinization works in terms of the variables that we care about, iron oxidation and hydrogen production. Serpentinization adds water to olivine, oxidizes iron, and produces hydrogen. So along the bottom axis here is LOI, which stands for loss on ignition, which we often use in lieu of a measurement of actual water content as a proxy for water content. It is known to be tends to be slightly higher than water content due to potential other volatiles in the rock, or H2O weight percent as directly measured. And these are all rocks acquired from either seafloor systems or from drill cores obtained from those systems. And sorry, there's no citation here. This is from a compilation put together by Lisa Mayhew. And so the ferric iron over total iron ratio here increases as we go left to right. So as we increase the amount of serpentinization. So indeed, serpentinization increases left to right until we end up with the approximate water weight percent of the mineral lizardite labeled across the top here. And then iron is being oxidized at the same time. We go from a rock that is indeed basically pure olivine or olivine with some pyroxene, in any case, essentially anhydrous and mostly reduced iron, to something that looks a lot like that. So serpentinite under the microscope that is at the same time producing hydrogen gas. And so we can easily calculate based on the weight percent of iron in these rocks how much hydrogen they produced. And so this is a compilation again from Lisa Mayhew and others in 2020. And what you see is as we go from left to right, we end up producing on the order of 0.2 to 0.5 moles of hydrogen per kilogram of rock serpentinized, which is not a particularly meaningful number until you put it in context globally. And that's here. So global serpentinization indeed produces a lot of hydrogen gas. This is a compilation put together by Barbara Sherwood Lawler and others in 2014. So based on her tabulations, and again, these are all estimates, and you can see the uncertainty in the measurement by the fact that slow spreading ridges, those where indeed we expect serpentinization to be occurring, is either more than or about the same as the total oceanic crust. And basalts apparently are producing significant amounts of hydrogen as well. So globally, this reaction between these nominally anhydrous mantle peridotites and seawater through serpentinizing systems is producing significant amounts of hydrogen in a way that we can expect them to impact the redox state of an atmosphere, particularly if we don't have a significant source of oxygen on the early Earth. And folks have tried, so this is Andrew Meredith working with the G-plates model to look at the production of hydrogen through time. This is across the bottom axis here, or across the bottom plot here. So depending on a need spreading rate, so somehow we need to tie the spreading rate to the hydrogen fluxes, and you can dig into Andrew's paper to get at that. But as we go, again, through time, we can see that there are variations in the total amount of hydrogen producing being produced, which are largely tied to the total amount of slow spreading ridges that we will see, oceanic transform faults. Okay, and based on some tide ratio of hydrogen to methane, so Andrew assumed that it's somewhere between 1 to 1 and 10 to 1, we can guess that the methane fluxes to the atmosphere are somehow correlated to the hydrogen fluxes to the atmosphere. And this is through geologic time. But if we think about Precambrian oceans, one major difference that might indeed impact the fluxes of hydrogen from these systems is the changing silicon concentrations in the oceans through time. So this is stuff that was originally thought about and published by Ray Seaver, who started us off today with that quote, and then eventually Conley and others from 2017 compiled it into a more recent data set. In any case, based on looking at the chert facies distribution and indeed some observations of silicification and also some observations of what appears to be silica gels precipitating on the Archean seafloor, we expect that the Precambrian oceans would have been approximately saturated with respect to amorphous silica. And indeed, this is labeled here as a diagenetic control. And through time, silica concentrations of the oceans would have decreased. So radiolaria and sponges evolve in perhaps late Neoproterozoic time or early Phanerozoic time, decrease the total concentration of silicon. They're important silicon sinks, but they're not as efficient as eventually diatoms became, where diatoms are incredibly efficient at reducing silica concentrations from seawater. They basically treat it like a nutrient. And you can, if you'd like, we can talk about it, or you can dig into the paper to get at this. But if we write this equilibrium here across the top between reduced iron serpentine and oxidized iron serpentine, we end up with silica as a fulcrum and hydrogen production as a independent variable that depends on that silicon fulcrum. So across the x-axis here is the activity of silicon in water and hydrogen fluxes or hydrogen activity through the top here. Sorry. And you can see today we're biased by the fact that modern oceans only have on the order of about 100 micromole silicon in them. So that's the water that's going into Precambrian or into modern hydrothermal systems at, for example, the Lost City hydrothermal system, and eventually venting and producing these activities of hydrogen as we see here. And indeed, these tend to correlate pretty well with the actual measured concentrations of hydrogen that we have measured at, for example, the Lost City hydrothermal system. But if we have higher silicon concentrations, approximately saturated with respect to amorphous silica in Precambrian time, we would expect that those activities of hydrogen in equilibrium with this iron serpentine assemblage would have been substantially lower. So Precambrian serpentinites would have produced on the order of about 2.5 orders of magnitude less hydrogen than modern serpentinites. There's lots of caveats and things to understand here, but indeed, this is an expectation that if we have high water rock ratio systems on the early Earth, they would have produced significantly less hydrogen. So this is a hypothesis. This is just a completely cartoon model, not based on anything real other than our understanding basically that this silica activity serves as a primary control on hydrogen fluxes. So in this plot, as we go from elevated silicon concentrations towards our modern low diatom controlled silicon concentrations, we can imagine that hydrogen fluxes move essentially in lockstep with that. So we start with, until essentially Neoproterozoic time, having muted hydrogen fluxes as a result of these low silicon activities in seawater, and then that increasing through time to what we see today because the diatoms are gobbling up all of that silicon. All right. And so why and how does this relate potentially to early Earth and potentially early Mars atmospheric conditions? So again, to reiterate, and I mentioned this briefly, this is I guess complicated atmospheric chemistry and atmospheric interactions. But the idea is that the methane, CO2, methane and CO2, H2 tend to absorb across parts of the spectrum where CO2 itself is not able to absorb heat, which again allows for an enhancement of the greenhouse effect potentially on early Earth and early Mars. And This is from another Wordsworth paper from 2017, where you can imagine heat coming into early Earth and early Mars could have been trapped, enhanced, trapped by not only the CO2, but also the methane and the hydrogen in the atmosphere. But hydrogen is a very leaky gas, so it's constantly leaking out of the top of the atmosphere. So Mars, in contrast to Earth, never really had a strong magnetic field, is much smaller, gravity is much lower, and so it loses hydrogen very rapidly. So if we're going to build up hydrogen in the atmosphere, it is going to be lost also quite rapidly as well. And so the mantle iron concentration is actually a strong contrast between Earth and Mars, and then potentially, as we look beyond Earth and Mars to exoplanets and even icy moons in our solar system, this actually dictates how much hydrogen you can produce during water-rock interactions. So we have here just a simple schematic from the Catling and Casting book, which is after work between Bernie Wood and John Wade, published earlier. And what you can see is basically the amount of iron that ends up in the upper mantle, which is the stuff that goes to produce melts, and also the stuff that goes to produce mid-ocean ridge, slow spreading systems where we're serpentinizing rocks from the mantle. If we very basically change the redox state of the mantle at the time of core formation, we change the amount of the total iron that ends up in our mantle. So the eruptive iron concentration depends on the oxidation state during planetary accretion. And a strong contrast here is the fact that Earth's mantle, upper mantle, apparently is more iron poor than Mars's upper mantle. So here is olivine mole fraction of iron here, and plotted against silica weight percent as just a variable to plot against on the x-axis. There's a terrestrial mantle. We all know this and love it. It's Forsterite 90. So Forsterite's the end member. So we're about 90% end member Forsterite, 10% end member phaelite, which is up there. So basically, any hydrogen fluxes that come out of our mid-ocean ridge hydrothermal systems, particularly the serpentinizing systems, must be reworking this very small amount of iron that's in this rock. If we go and look at rocks from Mars, so not only those analyzed by the CheMin instrument in Gale Crater, but also those that have been brought to Earth via Martian meteorites, we can see that those rocks tend to be much more iron rich than those of the mantle. And indeed, all of them, even the most iron poor ones, are substantially more iron rich than those of Earth's mantle. And if we want to go and find rocks like that here on Earth, we have to actually look at very interesting Precambrian rocks. So the ones that I focus on, again, having done my PhD in Minnesota, I spent a lot of time driving up to the North Shore, were those of the Duluth complex. So these are olivine-rich rocks of the Duluth complex troctolitic series, which they vary because it is a layered intrusive series. There is varying amounts of olivine in these rocks, but some of them tend to be on the order up to like 80 to 90%, and some of them are significantly lower than that. So serpentinites of the 1.1 billion year old Duluth complex can help to constrain the greenhouse on early Mars. So that's the main goal of this study that we published in Science Advances a couple of years ago. But ultimately, another interesting avenue for research is how this might have contributed to Proterozoic atmospheric redox as well. So here again is those plots of the ferric iron over total iron in typical mantle serpentinites over the past that we have obtained from rocks that are preserved on Earth's surface today. If we then layer on top of that the Duluth complex rocks, you can see that, as my high school history teacher used to say, the more things change, the more they stay the same. The ferric over total iron ratio in these rocks basically is identical no matter how much iron is in those rocks. So we expect that as we serpentinize a Duluth complex or a Mars peridotite rock, we will basically do the same amount of oxidized iron production as a ratio of the whole. But those rocks are much more iron rich. So they tend to produce on the order of 5 times more hydrogen than the rocks of our typical serpentinizing systems that we look at when we look at rocks from Earth's mantle. Okay, and they're also producing, so not just magnetite, which is a primary ferric iron sink, but also this other strange serpentine mineral, Hissengerite. So even if Mars is only weakly serpentinized, serpentinization would have likely played a significant role in its biogeochemical evolution. This is Beth Ehlmann's original publication on the potential for serpentine on the Martian surface. The stars are the places where she definitely identified serpentine, and you can see there's not so many of them, which for me as a person that thinks about serpentinization was kind of sad. But as Tosca and I showed in 2023, if we look a little bit harder and look for this other mineral, hyssodorite, not just the classic lizardite or chrysotile or antigerite, we can see that there's likely a much more abundant occurrence of not only this is all places where we've mapped and found ferric iron minerals, where you have ferric iron in the octahedral sheet, similar to hyssodorite, but also that in some places those occur in locations with high magnetization, which is this red color here. And the reason that there's not a lot of circles or any circles in this place that's covered by the gray is those are places of the Martian surface that are covered in dust and hard to see minerals. So serpentinization-driven hydrogen production warmed the Martian surface, but that rapidly escaped into space. Its low gravity and lack of magnetic field causes hydrogen to be swept off out into space. And indeed, you can go and look back at our Earth today and see hydrogen. So this is Lyman alpha radiation here, showing that we are actually leaking hydrogen into space around our own planet. And we do have a magnetic field and we do have higher gravity. So Mars would have been significantly worse. Okay, to wrap up, I want to come back to ingredients a little bit here at the end. So habitability is a prerequisite for life. I've talked a little bit about how we can make the planet warm enough using hydrothermal systems. Talked a little bit about pH. Of course, water is required for all of this stuff to occur. Energy coming out of these systems, light and heat, particularly heat. Water is the significant transporter of heat from the mantle up into the surrounding ocean. And then the site of venting is a site of heat interaction, an interface of heat interaction with the water lying above. And again, they harbor ecosystems today. But I want to point out that one of these things that's sort of one of the issues that we've been having in studying hydrothermal systems and their potential to have originated in host life is that they contain very little phosphorus. So this is phosphorus here in micromoles per kilogram. On the order of about 2 micromoles per kilogram is coming out of global vents if we take the average. And again, there's not much standard deviation there. So it's about 2 micromoles per kilogram, which is effectively what the phosphate concentration of seawater is within spitting distance. And Sharoni and Halevi have put models of phosphorus fluxes or phosphorus in seawater through the at least Phanerozoic time together. And you can see that we don't expect that the phosphorus coming out of these systems and going into water would have been going into seawater would have been much different at any point, at least over the last 500 million years or so. That the phosphorus concentration of the oceans is low, phosphorus concentration coming out of the vents. This is from Randolph Flagg and others on the right-hand side is about the same. Hydrothermal vents simply don't seem to have been, or at least high temperature hydrothermal vents don't seem to have been a significant source of phosphorus fluxes to seawater for at least Phanerozoic time. But as Drew Severson showed in this 2023 paper published in GRL, anoxic low temperature hydrothermal systems can release abundant amounts of phosphorus. And the mechanism here is quite simple. Because we're not forming ferric oxyhydroxides during the interaction of water with oceanic basalts, we aren't creating that surface for sorbing the phosphate that typically moves through these systems as originally proposed and shown by Bob Berner in the 70s. In fact, because we're not making those ferric oxyhydroxides, that phosphorus is free to go up until basically vivianite solubility or apatite solubility, depending on calcium concentrations. In more recent work, this is published by Adam Stone, who's a PhD student with Kim Lau at Penn State, basically showed that if we don't have our ferric oxyhydroxide absorption, that the phosphorus fluxes from these systems, low temperature weathering systems, would have been strongly controlled by the host rock calcium concentration, such that we see our typical phosphorus fluxes that we see today being on the order of 10 to micromoles per kilogram, and that being reduced as we increase the amount of calcium. And the amount of magnesium in seawater also plays a strong role. I encourage you to look into that paper to try and understand that a little bit better. All right, and finally here, just thinking about the tectonic implications for all of these systems. Plate tectonics defines our understanding of seafloor hydrothermal systems. Even saying the words mid-ocean ridge hydrothermal systems implies that we're thinking about plate tectonics. So we probably need to reimagine how hydrothermal systems operate elsewhere in the universe and take our observations of modern seafloor hydrothermal systems and view them through the right lens. So indeed, as we think about our systems here, that we likely would have had these low temperature weathering systems that I just discussed in terms of the low temperature basalt fluxes, but we wouldn't really have had, at least before the advent of modern style plate tectonics, what we consider to be an on-axis system. We would have expected something closer to a seamount, as I'll mention in a second. So oceanic core complexes, this is what hosts the high temperature rainbow hydrothermal field and the low temperature Lost City hydrothermal field on the mid-ocean ridge today, are a unique consequence of plate tectonic processes. We have seafloor spreading. That's how we get rocks from the mantle up and make these exposures on the seafloor. Without plate tectonics, we can't have these. Indeed, here's the Lost City hydrothermal field. It is this inside corner high here where we can see the fact that those mantle rocks are exposed to the seafloor is uniquely tied to the Atlantis transform fault occurring there at the mid-Atlantic ridge and pulling those rocks up from the mantle to the seafloor. So we can expect that this particular style of hydrothermal venting that we see at Lost City, which many have focused on as being a key element to potential theories linking these systems to the origin of life, could not have existed, at least as we see them today. We would have expected different geometries entirely. So I suggest that we consider instead intraplate vents. For example, the study by Malesi et al. Is focusing on intraplate vents and the potential hydrothermal systems created there, and their fact that the vents are actually being venting at quite low temperatures relative to these high temperature hydrothermal systems. So again, I would focus indeed on these intraplate vent systems as we move forward in trying to constrain Archean and potentially Hadean hydrothermal systems. And if you follow the tectonics literature, this interesting paper by Rosas and Koranaga suggests that these seamount systems likely would have become exposed and shallower with increasing seafloor age on the early Earth because of the interesting mantle dynamics at that time. So again, ripe for further investigation. Okay, so to wrap up the presentation today, I hope I didn't ramble over too many different topics, but hopefully there's lots of fodder for questions, is that hydrothermal systems play a defining role in generating habitable worlds. Secular and planetary changes in the chickens here, partial pressure of CO2, calcium concentrations, sulfate concentrations, silicon concentrations, likely affected the eggs here, permeability, pH, metal, phosphate, hydrogen, and hydrogen sulfide fluxes. But plate tectonics defines our understanding of mid-ocean ridge hydrothermal systems in a way that many of us might not actually have thought too much about, and this paradigm likely needs to be reimagined where plate tectonics is not operational. So if you have questions that I'm unable to answer over the question period, I encourage you to look at this just out, I think over the last couple of weeks here, volume of the AGU monograph series that came out of this AGU Chapman conference in Cyprus, and Tosca's and my chapter here 14. So, yeah, open for questions.
Great. I think we have question from Paul.
Yeah, excellent talk, very stimulating. I have two questions. The first one is that the oceanic crust on the early Earth would have been much thicker than modern oceanic crust, and the Archean probably more than 20 kilometers thick because of the higher mean mantle temperature. That would mean that the mantle peridotite would be much less accessible to seawater. Has that been considered in the estimates of hydrogen fluxes on the early Earth?
I don't think that particular aspect has been considered, but I intentionally didn't present it. My PhD student, Serhat Sevgen, has been working on barberton komatiite serpentinization reactions, and there's a whole lot of coupled processes there. So I think the way that the komatiite sequences at least appear in the rocks that we've studied from barberton is that, you sort of go through this process of top-down serpentinization, which ultimately seems to lead to silicification of the stuff that's right at the seafloor.
Hmm.
And then it gets paved over again, and then you do the same thing again. So I agree that the fact that it's thicker suggests that we're probably not getting those deeper rocks at all, and especially if we're not making core complexes, we're probably not ever exposing those rocks to seawater. And then the stuff that we do serpentinize sort of goes through a different pathway than what we see today, because it is sort of this interesting top-down process where we're infiltrating water, converting it to minerals as we go, and then ultimately creating what seems to be muted hydrogen fluxes for various reasons, which has to do with the chemistry of those interesting magnesium-rich eruptive rocks.
Right. My second question concerns the sulfate concentration in early seawater. And have always been curious about the presence of seafloor barite, barium sulfate, in Paleoarchean rocks in the Pilbara in northwestern Australia, the famous North Pole barite. And I read somewhere that even with an atmosphere in which oxygen is absent, sulfate can be produced, catalyzed by sunlight. Do you know if this is a significant process that might lead to more sulfate in early seawater than we would otherwise expect?
Yeah, so that's a great question, Paul. And I think probably 5 years ago I would have said, no, that's crazy sauce, right? But I like now that I work on the Curiosity rover team, I could tell you that every single sample we've ever drilled on Mars, which never had oxygenic photosynthesis, contains calcium sulfate. Every single one, right?
Yeah.
So like there must be a way to make it without oxygenic photosynthesis. And those barites are super interesting. And at the Chapman conference, Desiree Roerdink was presenting on her results, which has largely been focused on studying those particular um, barite deposits. And I think it seems like you can make them in the same way that where we make particular mineral sets on the seafloor today, where it's not really the locus of black smoke or venting that you would make those, that it's sort of like either a slight mixing or a slight cooling of the solution. And then that barium, as we all know, whenever we try to make sulfate barite to make sulfur isotope measurements, you could see how you could just put in a little bit of barium, and that barium just sucks up all of the sulfate, even if the sulfate's really, really low. So I
Yeah.
think I think that's what's happening, that you just have that particular set of conditions, and then that barite's ridiculously insoluble, so it gets preserved.
Yeah.
Yeah.
Good.
Thanks. And Greg has a hand up.
Yep. Paul anticipated my question. The barite in the North Pole has been a concern of mine for quite some time. You don't really get that in the modern hydrothermal system anywhere. It's anhydrite or gypsum, right? And on Mars also, we don't get it. Um, you hinted at these systems in the Archean maybe being lower temperature, maybe on land, and Paul sort of hinted maybe under sunlight. Is that the difference, or how do you explain barite?
No, we do get barite today. It's always just weird, right? So I think if you talk to my Canadian colleague John Jameson, like part of the fact is that people only sample the vent, right? They go and get the
Right.
chimney and bring that back up to the ship. But if you go and look at the other stuff around it, you do end up with barite in some of those rocks. So it's not that it's never there. It's just that it's weird, and it's not the most spectacular thing that people want to pick up.
Yeah, in marine rocks. It's just a tiny amount. The biggest concentrations of barite that I know of are actually in soils, uh,
Yeah.
in the sunlight, and I think partly created by sulfur oxidizing bacteria. Um, is that it? I mean, the barite in the ocean is a tiny amount, traces in marine rocks and in marine evaporites as well. But in
Yeah.
soils, it can form great nodules.
Yeah. Yeah, I mean it's barite's one of those minerals that's so insanely insoluble that if you have some barium and some sulfate around, you're going to make barite, and that's just how that goes. And I think Yeah,
I see.
always volumetrically, calcium sulfate is going to be more significant, more substantial than.
So you're arguing that it's inherited from barium sulfate in maybe some granitic system or some VMS deposit or something. But that's certainly not true for the soil examples that we know about. It's not inherited from a magmatic precursor.
Yeah, I don't know exactly. I'm not a barium cycle expert, but I think if you make a bunch of barium, or if you move barium even at micromolar concentrations, that it wants to titrate out sulfate until the barium's gone, basically.
No, I realize it's an unfair question. You didn't mention barium, but it's fascinated me. So thanks so much. That was a really good answer.
Baryte's extremely insoluble, so it can never be in high concentration.
Right.
But in soils it is, isn't
Yeah,
it?
I mean in seawater.
And in some magmatic systems, I don't know what they are, pegmatites or something. Yeah, you get barite minerals there too.
That's where you have two. That's where you have two fluids that interact.
Yeah.
One's bearing sulfate and the other's bearing baryte,
Right,
barium.
right, right. Yeah, fascinating. Thank you.
Ben maybe ask while our people
Yeah,
thinking about.
Francis, I think, had his hand up.
Francis.
Oh, Francis. Okay, go ahead.
Hey, thanks. Great talk, Ben. I really enjoyed it. I was curious after reading Danica Adams' recent paper about hydrogen production on Mars. She suggests that, over, I think it was about 40 million years of intermediate water on the surface was enough to maintain the hydrogen flux. But she was referring largely to low temperature oxidation and hydration reactions. And I was wondering if you could just have a few comments about the serpentinization reactions versus these lower temperature hydration alteration reactions for hydrogen production.
Great question, Francis. So there's a couple of unique caveats which I didn't really want to get into here because it's really complicated. But these iron-rich olivines are stable to much lower temperatures than the magnesium-rich olivines, right? So normal seafloor serpentinization, serpentine in is about 350 degrees. For these ones in the Duluth complex, it's maybe 200 degrees or something like that. So you can't really even start the progress of the reaction until fairly low temperatures, at which point the kinetics of the reaction are becoming much more sluggish, right? So there's this whole process where you can't even start the reaction until it's fairly slow. And then after that, it's sort of a continuum of potentially doing traditional serpentinization reactions or alternatively doing hydrogen production reactions. So if we have observations of this mineral hissengerite, so folks have really gotten excited about this observations from the Duluth complex of hissengerite serpentine solid solutions because until then, like largely hissengerite was observed as sort of this ratty, very amorphous phase that we're having a really hard time constraining because there's no sort of type examples of it unless you're looking at a TEM cross section of it. So part of that is like you can likely form this mineral hissengerite all the way to fairly low temperatures. And it seems like, and I wrote about this in the recent elements chapter with James Leong, it seems like if you have a lot more iron around, you can do a lot more magnetite production than you do in normal mid-ocean ridge hydrothermal systems. So this canonical rule that you can't make magnetite below 200 degrees Celsius in serpentinizing systems apparently does not apply when you have lots of iron around because you can just partition it into magnetite in addition to the serpentine in a way that you can't in those systems. So in the paper with Tosca about Mars, we did talk about the required advance rates of serpentinization reactions needed to overcome that hydrogen escape to space. And the numbers turn out to be pretty reasonable, right? So if you're just using low temperature, basically not quite weathering, but low temperature kinetics of olivine dissolution and serpentine precipitation reactions, you can end up with a number that suggests that you can make enough hydrogen to fill up the atmosphere, at least temporarily, by just running those reactions forward at advanced rates that have been observed in the field around the world. So I don't disagree with that possibility. The worry is always, and it depends on the stage of Martian history. The worry is that if you have a time in the history of the atmosphere where it was fairly oxidizing, and you bring oxidizing fluids into the system, you have to get rid of all of that oxidizing power before you can start making reducing power at the same time. So there's a lot of moving parts, but that's sort of how I think about that.
Yeah, maybe that's why they were suggesting this back and forth between reducing and oxidizing environments as
Exactly.
well. Yeah.
Yeah.
Okay.
Anytime you build up the
Right.
hydrogen, it's like it's ready to go. So,
Yeah.
yeah.
Thank you.
Okay. Ben, I have two questions, but maybe they're related. So my understanding in modern hydrothermal systems, you precipitate anhydrate in downflow systems, and in upflow system, you actually dissolve it. And so related to it, like about 15 years ago was paper by Lee Camp and Bill Seyfried about more shallow mid-ocean ridges in Precambrian. And I'm wondering if you have more shallow ridges, you might have a boiling in subsurface and you would precipitate sulfites in subsurface and clog the upflow system this way. So do you have any thoughts about it?
Yeah, great question. So the anhydrite really precipitates in two zones, which again was shown by Angus Fotherby's model in addition to, actual seafloor observations. One is, again, as you just heat seawater, it'll precipitate anhydrite. That was the stuff that was originally shown by Bischoff and Seyfried. But also, as you mix that upflowing hydrothermal fluid with seawater, it will precipitate anhydrite as well. That's why when we're at, for example, TAG or any real chimney system, there's a ton of anhydrite there in addition to the sulfides. It's because it's just titrating it out of seawater effectively.
Mhm.
Now, the question about low or shallow hydrothermal systems and temperature and fluxes is a fun one, and it's one that, again, my student Serhat Sevgen has been thinking a lot about. The idea is that if you watch Don Lowe's VSPG from earlier this year, if the Archean comadias are actually quite shallow, then you really can't get them that hot. Like they actually don't want to go that hot because you boil at much lower temperatures, and then you actually move that fluid out of the system because its flexibility is much higher, much faster. And there's all kinds of interesting solubility things that happen near the critical point, especially with minerals like or elements like iron. So I don't know that the clogging part that you perhaps mentioned would be different. I haven't really thought that through, but what I expect is that you would end up with different solubilities and different fluxes simply by virtue of the fact that you're boiling at lower pressures and temperatures.
Thank you. Okay, any other questions for Ben? Okay, if not, we have last talk in a week by Brenham Keller, and he will talk about sort of great unconformity, and after it we take a break and reconvene in early January. Okay, see you all next week.
Okay, thanks everyone.